Kia ora and welcome to video 6 in the series Insightful Integration. In this problem here, well, the formulas just blow up in your face there. In this problem, we're looking at another area problem, in this case, the area of a region enclosed between a circle and a hyperbola. The integration itself is quite messy because of the nature of these curves. The equations themselves are quite simple, but as soon as you've got square roots in there, the integrals become a bit messy. But fortunately, you don't need any substitutions or any trigonometric identities because you're given the formulas there. You just need to know how to use them. So, as always, give the problem a go, and then we'll see you after the intro music for the working through.
Alrighty, so this problem tests your understanding of how we can use integrals to find areas. It also tests your understanding of limits and what limits to use when finding the areas, but in terms of the antiderivatives, they're both given to us. So fortunately we don't have to derive those, although you might want to try that as an aside. The first one's a pretty standard result. You get that when you integrate a circle. The a squared minus x squared comes from if you have a circle x squared plus y squared equals a squared, and you rearrange it, so you end up with y equals the square root of a squared minus x squared if we consider the top branch of the circle. So if we go, there's a top branch there, radius a. Now that coordinate there, I can describe it in Cartesian coordinates as xy, or I can describe it in polar coordinates as a cos theta, a sine theta. And then that there is the substitution you make, that there's your substitution that you're replacing for x when you integrate, and you also replace the dx part, and it falls out quite nicely. So if you want to derive those results, then give them a go, but you don't need to for this problem. Okay, first thing we need to realize is that that first integral is related to the circle. And a circle, the a squared part is 7, so we're integrating the square root of 7 minus x squared. And if we integrate that from, let's say, 0 to the limits, and it turns out that the limits, that limits x equals 2, you can prove that using simultaneous equations. You just add the two equations together and get 2x squared equals 8, x squared equals 4, therefore x is plus or minus 2. If we integrate between 0 and 2 underneath the circle, we're going to get all of this area in here, 0, 2. And then if we take away the integral using the hyperbolic equation between this dude here and 2, we'll get that. We need to remove that off the area we calculated. So let's take away, now that lower limit is the x-intercept of the hyperbola, so if we make y equals 0 with the hyperbola equation, it comes out as 1. So we're going 1 to 2 of the hyperbola. So x squared minus, actually no, apologies, we got to rearrange this, so we've got y squared equals x squared minus 1 is the equation. Yep, x squared minus 1. Cool, so that's the area, and then we need to multiply the result of that by 4, or we just go 4 lots of this minus 4 lots of that, given that all we've done is found that area there, and we'd have to times it by 4 for the whole shaded. Okay, so then it comes to using the antiderivatives themselves. So the first one, 4 lots of the antiderivative. Be careful that you make it 7 minus x squared and not 7 squared, because a squared is 7. You also need to make sure you're in radians. So this is going to be x over root 7. Okay, so that's the first antiderivative, and we're going to evaluate that between 2 and 0. And then we need to minus 4 lots, and we do the other one. This time a squared's 1, What an absolute mish this would have been if we had to find those antiderivatives. And that one's between 2 and 1. Okay, so if we do all that, we end up getting, this slot here is 18.9272, and I've times that by 4 already, and then we're minusing off the second one, which is 4.2943. I worked that out earlier, but those are numbers you can use to check that you substitute in correctly. All we're doing is substituting the 2 into the x value, and then substituting the 0 in and minusing them. So standard antiderivative work there. And then that gives us a shaded area of 14.63 to 2 decimal places. Alrighty. See you in the next one.